To understand Astra, we should first understand what Vanguard is and what we're trying to achieve with this new program. So Vanguard is an advanced architecture prototype systems program which spans multiple potential projects. And the idea here is we want to investigate and prove out the viability of advanced technologies, both in hardware and software, for supporting the Department of Energy's integrated codes, and to do so at scale that is necessary. We really are trying to expand the HPC ecosystem as much as possible by investing in and developing on previously unproven technologies. We really want to push technologies in which we see as potentially valuable and impactful to our codes, but also we want to expand upon the number of choices we have when it comes to purchasing large HPC machines. Really, we're trying to buy down the risk and increase the tech options whenever possible for future large-scale platforms. We want to accept higher risk if that's necessary to do, and to do so in the Vanguard program to help mature technology solutions quicker. And again, this is always in the context of both hardware and software. So in looking at the Vanguard program, we first targeted ARM. So where Vanguard fits. So if you guys are familiar with the Department of Energy, we procure very large leadership class HPC machines, previously petascale and soon to be exascale machines. These are usually first of a kind advanced technologies, or historically they've been first of a kind technologies. But they're also meant for production cycles immediately. On the opposite side of the spectrum, we have test beds. And we have many different test beds. Basically, if there's any new architecture or CPU that looks potentially viable for running HPC codes on, we generally will get it and try it out and give it a go. But this requires both brave users and, mentioned here, brave system administrators as well. So Vanguard's meant to fit somewhere in between here. The idea is that we want to be able to experiment with a larger scale than we typically get from just buying a couple dozen nodes. And we really want to focus our effort on making sure that given technology can be matured to eventually impact the ATS or CTS large leadership class style machines, and demonstrate the viability for production cycles, and hopefully then be able to get production cycles out of these resources. So like I said, we've focused first on ARM. Sandia actually has had a long history with the testbed program for investigating CPUs in this platform for a while now, going back to 2014 when we originally picked up Xgene. This has since stepped up with various Cavium Marvell chips, as well as the HPE's Comanche program, where we had a small testbed system. Now the jump recently has been to this Astra system here in 2018. So, all right, Astra. This is I think we're able to call it the first Petascale ARM supercomputer, the first real supercomputer on the top 500 that is purely an ARM resource. It is 2.3 petaflops peak, which in the grand scheme of things is not very big if you look at the top 500, but that's not, the HPL is not always what we really care about. What we end up caring about a lot more is the peak memory bandwidth of this given machine, and we get a lot of memory bandwidth as well as just plain main memory in this regard. So the entire Astra program was meant to really, as I said, prove out the viability of ARM, and we named it appropriately, through difficulties to the stars. Turns out we've been more successful than I think we've thought originally, but we're still working out some things. And really, again, this is to demonstrate the viability of this architectural type for the U.S.'s Department of Energy supercomputing needs. All right, so what makes up Astra? It is 36 compute racks, or 9 scalable units, which consists of a little under 2,600 nodes, or a little over 5,000 individual CPUs. They are bundled into 72 nodes fit into a given rack, or 18 chassis, and then we have a 2U chassis which holds 4 basically half-U blade type compute nodes. Within a given compute node, we've got a dual socket Cavium Thunder X2 CPU. These are the 28-core specs running at 2 gigahertz. And we've got 8 DDR4 controllers per socket with 8 gig RAM, 8 gig DIMMs. And also on each compute node is a Mellanox EDR ConnectX-5 OCP card running what used to be Red Hat 7.5, which has now been upgraded to 7.6. So to dive a little bit really quickly into the node architecture, and this is sort of starting to highlight why we find this to be a really compelling architecture, is the fact that we have 8 DDR4 channels per socket, and those are connected to, to each socket. We then have from there dual 8x links, PCIe links to the Mellanox ConnectX-5 card, and then an EDR link obviously out, as well as a management network. And the fact that we can put all of that, we can harness all of that memory bandwidth on a given node is a really compelling architecture. So from a network standpoint, this is a 2-to-1 taper at the L1. So we have these very large cabinet size port switches, and then 108 level 1 switches. So taper at the L1, for instance. So we're able to push a pretty good amount of network bandwidth and have a fairly large fat tree network in this current configuration. From a cooling standpoint, this is a little interesting. So well, I didn't mention this, we actually put Astra, this new machine, into a brand new data center, which actually proved to be its own set of challenges. Future note, don't try to build a new data center at the same time you're trying to build a new machine. Do one or the other, potentially not both. But we're housing this through the use of something called so in this new data center we have a thermosiphon, which allows us to reduce our water for evaporative cooling for the majority of the year. And this is cooling 1 megawatt or a little more than, I think 1.2 megawatt is our wall plate evaluation, so essentially 1 megawatt for the machine. And doing so with a high amount of efficiency and reducing the amount of water that is required to run this machine, which in a high desert such as New Mexico is rather important. So if I'm not a thermosiphon expert. I don't think anybody cares too much in this room, but if you are interested, there's some really cool work between NREL and Sandia on this that there's a link there. So that's the machine overview in a broad sense. Now I'm going to dive into something that we call ATSE, or really our focus from a software standpoint, and where we're trying to drive this ARM ecosystem. So it goes without saying that we really figured we needed to invest from a software standpoint just as much as the hardware standpoint to really prove out the viability of ARM for our supercomputing requirements. So and this requires running our production codes at scale. This takes a lot of work, as many of you are probably familiar with, in terms of hardening compilers, focusing on optimizations in math libraries, making sure the tools all work, that you have all your necessary third-party libraries as well. Our codes are rather demanding. We have a wide array of new and historical codes for HPC, ranging from old-school Fortran codes that we just need to work to very highly templatized C++ that result in, static compilations of gigabyte plus binaries and compilation times on the order of several hours to potentially a day. So these are, millions of lines of code that need to operate at scale. That's a large set of requirements when you boil that down to actually coming up with a software ecosystem to support it. So we sort of break down into numerous different layers. There's the programming environment itself. What's the set of compilers? What are the math libraries that you expect? What MPI libraries are available? Because MPI is still crucial to any of our supercomputing needs. What do we have to focus on from an OS standpoint? Reducing noise and jitter, for instance, are perfect things that really actually matter at this sort of scale. And ensuring that we have a usable job scheduling and management system, as most of these systems are still run as batch workload systems. So this is a little different than your traditional cloud where I can just spin up another instance. Typically with HPC resources, you see over 90% utilization of your hardware 24/7, 365. So this is not like we have idle CPUs sticking around here. So we use batch workloads to basically prioritize and to run through those workloads. And then, of course, there's a whole lot of work to do in system management. How do you boot these nodes? What do you want to monitor? And so forth. So with this, we came up with ATSE, or our Advanced Tri-Lab Software Environment. And the idea here is to define a software environment or a programming stack or set of programming stacks that can directly support our codes. This is an effort that we've led at Sandia across the DOE. It involves partnerships not only with our sister laboratories within the ASC, but also HPE as well as our primary vendor or integrator. The importance here is that while we have a version 1.0 and we're working on 2.0 of the ATSE software stack to support our workloads, we're hoping that this has a lasting value beyond just this individual machine. Essentially, we're also trying to communicate to the larger community and give back to the larger community our software requirements. We don't want to lock this all down. This should be open, which I can talk a little bit more about if we have some time. And we really want to test and validate that this, in fact, does support our workloads at scale. That's a really important thing. It's one thing to say, yes, okay, this all magically works. It's another thing to actually prove it and then to optimize that software stack again and again to really support the computing requirements that we have. So in doing this, we've leveraged the OpenHPC environment through help with Lenovo, replicating their open build service and putting together a set of RPMs and libraries to provide this software environment. So again, it's really important to provide this as an open and modular stack. This isn't something that we want to own. This is something that we want to be able to use as a tool for communication. If there's an optimization that can be had from the hardware, for instance, picking out the right set of optimizations to target our Cavium Thunder X2 chips, then we want to do that. We want to integrate that directly in our stack. If we want to be able to take advantage of the latest and greatest from the Mellanox OFED stack, we want to be able to do that. Or whatever other optimizations can be had from the vendors. If they want to improve upon this stack, we want to give an equal environment for those vendors to provide that value add when and where possible, and still have direct influence on our mission applications. So as I mentioned, we've leveraged several efforts, OpenHPC being the primary one. We're also building this on TOS, which essentially for the greater community is just Red Hat. TOS is an internal set of Red Hat libraries that we use with optimizations and some special sprinkles that are put in to ensure that we can run these at our various DOE laboratories. And we also want to leverage the what's called the ECP, or the Exascale Computing Project's efforts in developing advanced system software, so ECP ST projects directly into these into our ATSE stack as well. And we're working on doing that as for instance, the E4S effort spins up within ECP. And we also want to make sure that we provide an opportunity for some of the more emerging, what I would call emerging codes, AI workloads, some of the deep learning frameworks that are just starting to have relevance and take hold in our computing ecosystem, and making sure they also have an opportunity to work and to be proven out in the same prototype environment. So I mentioned a numerous set of aspects, and really we want to be able to be agnostic to some extent to your given operating system, whether that's something that is completely open and that you can run in a cloud environment, or something that is TOS, which has some proprietary bits as well as Red Hat specific features, or a completely closed vendor operating system that they've worked hard to optimize and improve for HPC. Cray architectures are a perfect example of this. and then be able to provide the same user-facing software environment on top of it that directly supports our application portfolio. And hopefully, we'd also like to not only provide, obviously, a native install that I have, on our actual Astra architecture, but also be able to have this in a container image that I can share or communicate or allow to, our developers to build off-site. So that's sort of where we're at today with Astra. There's a lot of things that we're also working on and eyeing in various degrees of success thus far, moving forward. So first, there's still some bugs. There's still a lot of, if anybody stood up these machines or a machine of this size at scale, you know exactly what I'm talking about here. There's still a lot of little itty-bitty details that you find, and you can only find them when you move to scale. So we're working on that. Every day is a new tool and a new challenge that we're finding and growing our success in that regard. This is, of course, one of the lead engineers in HPE's Apollo 70 division, and here's a rather large bug. In terms of, bringing up the machine, we've had a lot of success initially. And again, this has to do not only with the large ecosystem that we're able to leverage through our partners such as Lenaro, but also the fact that we've invested from a testbed level at this for several years. Our system was online technically 2 weeks prior to the data center itself being completed. We literally had to run around with hard hats for the first couple of weeks, initially booting and turning on this machine. This allowed us to, just within 2 weeks later, have submitted HPL runs on the November top 500 list. We obviously didn't have all the nodes online in time, but we were able to hit 1.5 petaflops of RMAX, which is just under an 80% efficiency, which is already better than some of our leadership class machines already. You can imagine we're going to see these numbers go up as more hardware has become available in the past several months for the ISC submission as well. And we've also been running some of our application ports and making sure that the key frameworks of interest to us are there and functional. So just a quick comparison and quick summary, basically. We've got various degrees of improvement, and these numbers are based on Haswell, so our Haswell series chips that we've deployed on Trinity. Trinity, I think, being number 7 on the top 500, something of that sort. So our big ATS production system that we primarily use today. So we're already seeing direct improvements and speed-ups over the Haswell and even Skylake chips as well. So one of the things that I care a lot about, and I'm trying to drive forward in particular, but this will also hopefully have a larger set of impacts or opportunities for impact in the broader community, is leveraging containers and virtual machines on ARM. This isn't really unique to ARM, but it's a great place where we can excel. So we've been working with Singularity containers primarily, and we have them deployed, the new Singularity 3.0 on our Astra machine in various stages of testing and validating that workload. And working with Scilabs, which is the new startup that's backing the Singularity Containers initiative and ensuring that these things work. It's not complete yet. I still have a lot of work to do, but we have basically that ATSE software stack in a container image, and we're hoping that we can distribute this. We plan on leveraging the Scilabs remote builder library, which is of critical importance because, sadly, I cannot go to Apple and hand them money and have an ARM-based laptop. So I can't yet do a Docker build. I can't build a container on my MacBook that I happen to have and have that run as is on Astra. So leveraging a remote build service where I can just add a -- remote build to my Singularity container and have that point to an ARM build node is something of high value for us on this architecture. This is part of a larger effort that we've put forth that we're calling the Supercontainers Project. If you're interested more in containers, come find me afterwards. We can chat all day if you want. And KVM is also important. I would say some of the utility here has decreased as we see an uptake in containers, but virtual machines are still very much important. And while we can run VMs, there's still definitely some work that we can do in terms of improving the performance of these VMs. There's plenty of other what we're considering R&D activities at this point as well that we hope to get to in the next year or two on this system. Evaluating parallel file systems and doing so at scale. So the Lustre client, we have a Lustre storage backend that's x86 based, and we have the Lustre client all working and mounting our Lustre file system on Astra today. And that has been successful with some of the latest Lustre ports. But boy, it'd be really nice next time, or hypothetically next time, there was a native ARM solution for Lustre. There's also plenty of other different file systems that we may be able to leverage. And again, these aren't unique to ARM, but the flexibility of the ecosystem allows us to chase these down with a little more veracity than potentially we could otherwise. So Ceph, BGFS, GlusterFS are good examples of this. We'd really like to leverage some of the improved MPI thread support. My next slide will go into this in a little more detail, and tag matching acceleration. And there's plenty of OS optimizations that still should be had. And these OS optimizations become critical as you increase the scale of your machine, in this case to thousands of nodes, as small performance perturbations or OS noise can have large impact on your application. This isn't processing 10,000 Google queries. This is executing one application but doing itty-bitty little bits of this application. If any one of those 1,000 processors slows because it's handling an interrupt, your other 999 are sitting there waiting. So OS noise becomes critical, and there's a lot of optimization that I think we can still have in this regard. MC kernel is a technology that's coming about through the Recon group, and we're very excited to try and take a look at this in the next couple of months here, if possible. So these are sort of several things that we're focused on, and I think we're hoping to collaborate with Lenaro and other SIG members on driving forward on these activities. Again, network performance. This is something that is critical to HPC and unique to HPC is often latency, and so we've enabled the sharp optimizations within Mellanox, and we're seeing latency improvements at scale. This being MPI all reduce. There is still some weird things that are happening, as you can see in this little jump here. Sorry, this is not a very good projector, but when you don't have sharp, you see these random perturbations in performance, but there's still a lot to go here. But so far, this is looking good. So with that, I'll show a pretty picture, which probably doesn't look very good on this projector, but I can take any questions. Sorry, guys, I know it's lunch.
With OpenHPC, any big breaks that you guys ran into and pushed back?
So OpenHPC is a great system that we've been able to leverage. However, our software cadence is completely different than what I would say OpenHPCs are. We can't go changing our compiler every couple of months because our developers will be furious when they've spent months porting to a specific, this particular architecture, and I move from GCC 7.2 to 7.3. That totally negates all their previous work. So we have to be very targeted and careful about, for instance, our software versions from our compilers to our highly optimized third-party libraries. So that's why it's a little different than OpenHPC, but there's also plenty of things that we've seen and found already in evaluating our stack that we've been able to pass back to the OpenHPC community. For instance, target optimizations for the ThunderX2 chip. We found a couple of things for running HPL using some blast routine. If you add certain compiler optimizations, we get like 4.5, 5 times the performance speed up. So that's just one example. We found a couple of other, OS bugs that have popped up at scale that, 1 out of 200 nodes will go out to lunch processing some random interrupt, and being able to track that down has been, and working with the OpenHPC community in that to try to replicate something that is rather difficult to replicate. But at least being able to report that and work with a community as a whole to sort of solve some of those little bugs is I think, a value add for everybody, hopefully. So. Any other questions?
So I'd like to ask you, what is the real advantage of the current processors for HPC, so from your experience?
So these do not have SVE. The biggest value add that we're seeing from these processors in particular is the memory bandwidth. So while we all talk about HPL and we all love to do top 500 runs, in fact, high-performance LIMPAC, so that's what evaluates. LIMPAC is basically matrix-matrix multiplication in short. And that is how we evaluate all of our current supercomputers today, for better and for worse. While it's an easy benchmark to run, it doesn't relate to our integrated codes very well at all nowadays. Maybe they did 25 years ago, but today our codes are much more memory bandwidth driven. So this is why benchmarks such as HPCG matter most. And if I flip back here, and HPCG is very much sensitive to memory bandwidth. Where's that slide? Which is why you see this is a really nice and balanced architecture for us and our workloads. Where, yeah, sure, we're, I believe on the top 500 we hit like 130th or something. But when it comes to HPCG, we're like 36, and I expect that number to drop for the next ISC iteration. That shows us that it's really the memory bandwidth, and also a high-speed, low-latency interconnect, in this case, the Mellanox. But the fact that you're able to get low latency all reduces at scale is something that's really important. So,
as you know, the AMD and the next version of the Intel is going to catch up.
Oh yeah, no, exactly. So Skylake, so this has the Thunder X2s have 8 channels of DDR4. Skylakes have 6 channels, but it's of no surprise that maybe these numbers will go up. So yes, that's certainly true. But for purchasing this machine 6 months ago, this was a very good architecture, well qualified for our codes. So memory bandwidth is an important thing. The more memory bandwidth we can get, the happier our codes are. So long as you have a balanced architecture along the way. So you want to avoid any small little straws in this very complex architecture.
So for next the exascale machine in your plan, what kind of things you're expecting?
If we were to look at, let's say, doing this again at a much larger scale, let's not even say exascale, I think we're going to, any way that we can get, more memory bandwidth is going to be a good thing. And any way that we can drive that memory bandwidth, for instance, with SVE and vectorization of codes to fully drive that extra memory bandwidth, seems like a win to me. I've been very much a supporter of the Fujitsu architecture. I think that is certainly compelling, the strategy in which you're taking. So in terms of what the first exascale machine will be, that's anybody's guess at this point. So I don't want to overly I don't want to get too caught up on that. But I will also say that we purposely did not look at GPUs in this architecture. Because it's easy enough just to add a GPU to this architecture and go from there. Really what we wanted to focus on is ensuring that our codes can work on ARM today. That's step one before we can really move any further with GPUs. You look at the Summit and Sierra systems. So these are Power 9 architectures with a whole bunch of really big NVIDIA GPUs, where the peak flops is driven, 90+% by the GPUs rather than the CPUs. But the code all still needs to work on those IBM Power 9s first. So we purposely didn't tackle this problem, in part because it's, I think, secondary. So how's that for a roundabout answer?
Well, you kind of took a question out of my next one was in the previous slide. You had the alignment with the AI ML workloads. Sorry, I'm losing my voice. So what is the focus for you guys? Is it going to be SVEs or SVE work that Fujitsu or Riken is doing, or do you guys think that there's going to be some other magic wand type? I was saying FPGAs. I don't know.
Yeah, I have no idea. I will say that our primary workloads are traditionally bulk synchronous parallel workloads. These are MPI workloads running at scale. This is the forefront of HPC's software ecosystem, has been for decades, and it probably will be for at least the next several years, and certainly into initial exascale machines. So I don't think that'll change. I think what we're seeing is that these workloads can be augmented through additional usage of ML workloads. Think of this as using ML to do application steering or in situ data analytics while my simulation is running. These are some of the workloads that we're starting to see take hold across the DOE, as well as doing some traditional DL training. But I would say those are more, I classify those as emerging workloads rather than mission workloads. How's that? So I hope that those technologies will impact and improve those mission cycles when and where necessary, but they're not the drivers at this point. So, anything else? Cool. Well, thanks, guys.